Testing. Welcome back, class. Today we're going to be beginning Chapter 9. We'll be doing Section 9.1. I'll be assigning that at the end of this video. That Section 9.1 would be due on Monday. I believe it's March 30, if I'm not mistaken, on Monday. Before we begin, there is a set of notes under content in Blackboard. The set of notes is entitled Elements of Hypothesis Test. If you haven't loaded that or copied it off, it might be good for you to stop the video now and either load it or copy it off, because I'll be referring to that off and on during the lecture here today. For those of you that already have it loaded or copied, I think we'll start here. A quote that comes to mind here, especially in this day of internet and all the information that's out there, is this quote: "In this country, you have the right to say anything you want, but you don't have the right to be taken seriously. You have to earn that privilege." There's a quote from George McGovern. Many of you were not born when this man was running for president. He actually is a graduate of Dakota Wesleyan, and he was here when President Greg Christie was inaugurated into his position here at the college. George McGovern, who was a former presidential candidate, one of the last two, gave the speech during that time. Again, he was a Dakota Wesleyan grad. But a good quote here, a good quote. Tests of hypothesis are all about earning that privilege to be taken seriously. Basically, it's a test, as we're going to see here right now. It's a standard procedure to provide mathematical evidence to refute one statement, which we call a null hypothesis, and then conclude another called an alternative hypothesis. It's basically a way that we provide mathematical evidence to verify what we're trying to say to an audience. Think of this testing procedure as a presentation you would give to convince an audience. It's used in business, it's used in the hard sciences, the soft sciences. It's a worldwide procedure that's used to give, again, mathematical evidence to emphasize or convince an audience of what we're trying to say. Here's an example. We may want statistical evidence to say the average number of hours worked on a part-time job by a Northwestern student per day is less than 3. Again, we could ask a student how many hours they work, and they might say 2.7, but that doesn't give me evidence that the true average is less than 3. This procedure gives us mathematical evidence to make proper conclusions. Here's a bunch of other examples. This is by no means an exhausting list. Suppose I wish to find out whether the average number of minutes a customer spends in my department store is greater than 15. Suppose I wish to find out the customer satisfaction rating for a service department. Suppose I wish to test the company's claim of a 50% drop in returns of a particular product you sell if you bought their marketing service. I wish to provide evidence the drug we produce does in fact relieve the level of pain in patients' experiences. We wish to provide evidence of a particular medical procedure is better than the one we've used in the past. Those are, again, just examples of that. What I'm going to try and do next is break down this page of notes that I talked about at the very beginning. I need you to understand the hypothesis tests that we're talking about. is a fairly difficult concept for a lot of stats students. It is very, very likely at the end of this first class period dealing with hypothesis tests that you're going to seem confused. Do not be alarmed if at the end of this video you're going, I'm not sure what he's been talking about. That is a very, very common response. We're trying to just introduce it here today, and hopefully as we work through many, many, many examples over the next week, you will start to get confident in the procedure and you will begin to understand the procedure more and more. You'll begin to understand what it means to give mathematical evidence to our statements. So for now, I'm going to break this apart, going through step 1, 2, and 3, etc. in a slow manner. So here we go. This is very similar to your notes, just broken down a little bit more. In step 1, we have to make both a null and an alternative hypothesis. The symbol we use for the null is H sub 0. It's a theory about specific values of one or more of the population parameters. What that means is we could be talking about proportions, we could be talking about means, we could be talking about the difference of proportions, and there's a gamut of other things population parameters could entail. The theory is stated something like this: H sub 0, some particular parameter, maybe the mean, is maybe less than or equal to 3 or 17 or whatever the problem might happen. This is kind of important to keep in mind. This hypothesis, meaning the null, this hypothesis is usually the opposite of what we desire to prove or show. This hypothesis is often, though, a claim from someone. So if someone is claiming something and we want to test it, we would put their claim as a null. We want to see if we have evidence to doubt their claim. This is, again, part of number 1, the null and alternative hypothesis. The alternative hypothesis, which is given this symbol, H sub A, easy to remember for A for alternative, it's a theory that contradicts the null. When we say contradicts, it means both of them cannot be true at the same time. Just a quick side note. If I want to show that some mean is, let's say, less than 3, if I can show that the mean is not greater than or equal to 3, then by process of elimination, I've shown that it has to be less than 3. That kind of logic where we're going to prove one of them false, hopefully the null, which then allows me to conclude this one, the alternative, to be true because they contradict each other. So if I can show that the null is false, then I know the alternative has to be true. This alternative generally represents what we will adopt only with sufficient evidence, only with enough mathematical evidence. We need to give strong evidence or very strong evidence to indicate the other hypothesis, that being the null, is false. When that happens, we can establish that this hypothesis must be true. Here's an important concept. Generally, this alternative is what we desire to show or prove to be true with some particular level of confidence, which we call alpha. Next, I would like to go away from that page of notes for a little bit. We'll come back to it. But we're going to look at 3 types of hypothesis, both null and alternative pairs. Okay, so 3 types. Here's the first type. If a bank manager wants to show or provide evidence that the average wait time for a customer in line at the bank is less than 6 minutes. I put in bold here for this first time, kind of what we're after. We want to show that it's less than 6. That's what we desire. We want to show that. So what is less than 6 is going to become my alternative. I'm going to put X bar is less than 6 for my alternative. I do that one kind of first, and then I go back previously and make the null. It would look like this. Here's my alternative. Remember I said the mean was less than 6. I wanted to show that the average time, that's the mean right here, mu, is less than 6. That's what I want to show. I made that into the alternative, which means then my null must be the opposite. So if this one said less than, this one must say greater than or equal to. This is one of the 3 types. It's known as the one-sided less than alternative, because right here it was one-sided, didn't go not equal to. It was either going to be less than or it's going to be greater than. This one was less than, one-sided alternative. It's one of the 3 types. Here's the second type. If a company wants to test or show or provide evidence, different ways of saying the same thing, in favor of the claim that the average breaking strength of its new trash bag is greater than 50. I wanted to show that it's greater than 50. So my alternative should be that. That's what I desire to show. So my alternative will be the mean is greater than 50. It looks like this. Right here is my alternative. Notice it's greater than 50. That would mean then the null must be the opposite. The null says the mean is less than or equal to 50. This is also one-sided because it's just going in one direction, greater than 50. Up here, this was one-sided. It was going in one direction, less than 6. It's one-sided, greater than hypothesis. These 2 types are the most common, but now there's a third type that is referred to as a two-sided one. Notice, I'll read it first. If a food company wants to test or provide evidence against the claim that the average weight of the contents of the potato chip bags is 12 ounces. Notice we're not trying to show that it's greater than 12, like we did here. We're not trying to show that it's less than 12, like here I did less than 6. This one is looking to see and test, is the weight, is it 12 inches? That's referred to as a two-sided one. One-sided was here just going to the right of 50. Here was one-sided just going to the left of 6. Whenever I have this is, it's considered a two-sided, meaning I'm looking to see if there's evidence that it's a lot more than 12 or a lot less than 12. Because this is a two-sided one, the two-sided ones in some ways are kind of easy because for a two-sided one, we always make the null 12. Or excuse me, I apologize. We always make the null equal. Always make the null equal to some number. The alternative is always making the mean unequal to some number. I want to say that again. For a two-sided one, the null is always the mean equals, and the alternative is always the mean does not equal. I'm looking to see if the sample gives me evidence that it's either so much bigger than 12 or so much less than 12. Either direction, either side, hence two-sided. If I can get enough evidence that it's so much bigger than 12, or if I can get enough evidence that it's so much less than 12, then I know that I have evidence that it cannot be equal to 12. That'll make more sense when we get into a bunch of examples. But again, a quick review of the 3 types. One-sided, less than. That was the alternative being less than some number. One-sided, greater than. That was the alternative being the mean is greater than a number. Two-sided means the alternative was unequal, means it could have gone either direction, either direction. I'm going back to this set of notes again. Hopefully you have it in a place where you can refer to it. We're looking at step number 2. Step number 2. It says to specify the level of alpha. That will be given in the problem in the vast majority of the cases. It'll say test at an alpha level of 0.05, or test at an alpha level of 0.01, or test at an alpha level of 0.10. Usually it'll be given in the problem. One of the important things to remember though is if it's not given, the default is always let alpha be 0.05 if it's not given in the problem. That 0.05 level for alpha is the level that's used most often in the business field. In the medical field, it is usually an alpha of 0.01 or 0.001. They want to be much more sure of their concluding statement in the medical field. But in business, alpha is usually 0.05 unless it's otherwise stated. 0.05 again is the default. Sometimes they'll give you multiple levels, but this alpha level is referred to as the level of significance. The value of alpha is also the likelihood of making a type 1 error. Now, right now, we haven't talked about that. We'll be discussing that a little bit later. But a type 1 error, as opposed to a type 2 error, we'll be looking at both. The type 1 error is usually considered to be the more serious one. That's why when we list alpha to be 0.05, means there's a 5% chance we'll make a type 1 error. If we want to be safer, we would list this alpha as 0.01, which means then there would be a 1% chance of making a type 1 error. We want to keep the likelihood of making a type 1 error low, because it's considered to be a very bad error. Okay? A type 1 error would be something like this. I'll talk about this in a moment. You saw this slide earlier. We just got done with it. A type 1 error is where I feel I've got enough evidence to reject the null and conclude that it's less than 6, when the truth was, it was actually greater than 6. We must have gotten a bad sample or something. That would be an example of making a type 1 error. A type 1 error is when I got enough evidence to reject the null and conclude the alternative. So in this example, a type 1 error would be I had enough evidence to believe that it is not less than 50. I concluded that it was greater than, when the real truth was that it was less than or equal to. A type 1 error here would be I had enough evidence to believe that it did not equal 12, and I concluded that it was unequal to 12. I might have concluded that it was greater than 12 or less than 12, depending on the sample. But the truth was, it actually did equal 12. I just happened to get a bad sample. Those are all examples of a type 1 error. We'll discuss that much more as we go on here today. Another component in this step 2 of your test, and we're looking at these components. I'm right here now in step number 2. One of the things that shows up is we list the sample size. So in step 2, we first specify the alpha level. Then I list the size of my sample. That's n might be equal to 10, might be equal to 50, might be equal to 500, whatever the sample in the problem gives you. We also select a test statistic. It is usually based on this sample, as well as what the problem might be talking about. If it's talking about mean or proportion or something else. For example, if I'm looking at a mean and my n turned out to be 20, the test statistic that I would choose would be a t, because I had a small sample, n was less than 30. If, on the other hand, n was, say, 100, that's more than 30, then I would say my test statistic is a z. That tells our audience what type of statistic I'm using and why I'm using it. We've looked at both z and t's so far. We'll also be getting a chi-squared later this spring. But there are other ones that are used in F statistic. I think we might have a chance to take a look at that as well. I'm continuing here with step 2. At this point, we're looking at 2 possibilities. If you look further down on that page of notes, you'll see right before 3 and 4, it says if using a critical value, and a little bit further down it says if using a p-value. That indicates there's 2 types of these hypothesis tests. So first, if I'm using a critical value rule, if I'm using a critical value test, then under number 2, I would list a rejection region. It's basically a null rejection region. This would be a rejection region that would indicate that our null was false. I will typically refer to it as my line in the sand, my line in the sand. Okay, let me give you an example here once. First, let's just say, I'm going to go back to one of those first examples where the null we had, if you remember, I think it was the mean was greater than or equal to 6, and the alternative was the opposite. The mean was less than 6. Visually, this is what's happening. I am testing against the value 6. I'm going to be taking a sample, and I'm hoping that the average of the sample, it should likely be around the 6. Okay? Now, I'm hoping to show that it's less than 6. I desire to show that. That's why I made the alternative less than 6. So what I'm hoping is that my sample is way over here someplace, way over less than 6. If it's far enough over, then I say I have enough evidence that I'm sure it's not greater than 6. If it's far enough over here, I can cancel this one off, say it's got to be false, and I can conclude that it's got to be less than 6. The question is how far over does that sample have to be for me to have enough evidence to indicate this is false and this one must be true? How far over? That's our line in the sand. That's my rejection region. So for example, I might say if the z-score goes past a negative 1.96, it goes to the left of a negative 1.96 z-score, then I'm going to say that's far enough, that's enough evidence for me to reject the null and conclude that it's less than 6. If my sample, say, hit here, or hit here, or here, we would say that's within reasonable variance of 6. We would say we don't have enough evidence to reject that one and conclude that one. If it falls in either one of these, we don't have enough evidence to reject anything. We tend to say we continue to assume status quo. It's only when I've gone over the line in the sand, in this case, that's my rejection region. I would say my rejection region here, RR for rejection region, would be my Z was less than this negative 1.96. That's my line in the sand. That's my rejection region. If my sample went over that, that's too far. That gives me mathematical evidence. By the way, you remember when alpha had a tail of 0.05, giving me 0.49, excuse me, 0.45, I apologize. I got that still wrong. I got to get these values straight, excuse me. 0.025, I apologize. 0.475. If you have those values, that gave you a 1.96. You remember that was a 95% confidence interval. Well, that 1.96 then had a 97.5 confidence level. If I went with a two-sided test, I would have used 1.96. One-sided test would have been 97.5%. That doesn't make a lot of sense yet, but it will in time. Okay? Determining that z-value to test against our line is coming from the sample. We get the z-value for the particular sample. We compare it to the rejection region to see if we went over that line in the sand. In step number 4, that's again from that page of notes, if I went over the line in the sand, I rejected the null and I concluded the alternative. If I did not go over that line, then I had insufficient evidence to reject the null and I continue to go status quo. These were steps 3 and 4 and a little bit added to 2. Here's the part that's important. If I was using a critical value test, okay? If I was using a critical value test. But now, if I'm using a p-value test, okay? I'm going to compute the value of the test statistic from the sample. That's again like saying compute the z, or in some cases it's a t. But if I'm using a p-value test, we'll be computing its p-value, hence the name of the p-value test. The p-value is the probability that you would have gotten that kind of sample. So p-value, almost think of it as probability of getting that z-score, or probability of getting that t-score, or whatever the test statistic happens to be. We take that p-value and we compare it to the alpha. Alpha, again, is our probability of making a type 1 error. So for example, let's just say in my problem, alpha happened to be 0.05. If I found a z-score to be some number, and I found its probability, its p-value, let's say the p-value was equal to 0.03. If the p-value is 0.03, which is less than my alpha, then I have sufficient evidence to reject the null. But if the p-value was, say, 0.09, that is not less than my alpha, then I would have had insufficient evidence. 0.03 means it's a less likely sample than 0.09. 0.03 means I would have gone over my line in the sand. 0.09 means I would not have. Then we either reject or not reject the null, and we interpret that decision in context. I'm going to do one problem now because I want to see the entire procedure at one time. I don't expect you to have this mastered after this one example, but I'm hoping after seeing this one example, some of the other things that we've talked about might make a little more sense. So take out that page of notes again and follow along steps 1, 2, 3, and 4 as I do this example. Suppose, because of an increased scholarships being offered, we wish to provide evidence that the average Northwestern student now works less than 3 hours per day. That's the average. If a sample of 50 students indicate that the mean number of hours worked per day was 2.9, standard deviation of 0.2 hours, use a critical value test to determine if there is significant statistical evidence, that's like saying mathematical evidence, to show that the average is now below 3. Let alpha be 0.05. Okay? Well, let's take a look at that once. First of all, I'm going to go with step number 1. This is coming off of that sheet. Step number 1 told me to list the null and the alternative. So here I go. Rather than listing the null first, H sub O, most of the time, most people will list the alternative first. The alternative is what I'm desiring to show. Let's read that again once. See if there's enough evidence to show the average is below 3. I'm hoping to show the average is below 3. So I'm hoping to show that the mean is less than 3. That's my alternative, H sub A. The null then has to be the opposite, which would mean then that the mean is greater than or equal to 3. There's my step number 1. I listed both the null and the alternative. Step number 2, I'm going to list the alpha level. It was given right here at the end of the problem, 0.05. Had it not been given, the default is also 0.05. Next, if you check out number 2, we're going to list the sample size next. N, in this case, happened to be 50, a sample of 50 right up here. Because N is more than 30 or more, and I'm looking at a mean, I'm using that central limit theorem, and I know that I'm going to be using a Z statistic. So I've listed my alpha level, I've listed my sample size, and I've listed my statistic. They told me to use a critical value test. Okay, well, that critical value test now has to give a rejection region, RR. So I'm going to look for what is my rejection region in this case. Okay, to help you see that, I'm going to take another piece of paper out so I don't waste so much space. But here's what's going on. My alpha level is 0.05. It's a single-sided test because it's looking to show that it's less than 3. So here's what's going on. I'm testing against the 3. I'm hoping to have enough evidence that my sample is far enough less than 3 that I have enough evidence to say that it's not greater than 3, has to be less than 3. I need this line in the sand right now. How far is far enough that I can say this is false and this one is true? That line in the sand is determined by my alpha level, 0.05. I put all of that 0.05 into one tail, which means this has to be 0.45. This is a little confusing now for this reason. When I did a 90% confidence interval, I had 5% in each side, giving me 90%. Those z-scores were a 1.645, negative and positive. That was for a 90% confidence interval. 90% means I took that 10% and I split it in half on each side. Listen carefully though now. Because this is a single-tailed test, going in one direction, less than 3, I take all 5% and put it in that one tail. So because all 5 is in that one tail, I could go to my chart and again look at 0.45. It's right in here. It's 1.645 right between those. That's where that came from. So that's the z-score. If I go over that z-score right there, then I have enough evidence to say it can't be greater than 3, or I don't believe it's greater than 3, and I now believe that it is less than 3. So I have to go to the over top of that line, which means less than that number. So here it goes now. My rejection region is z is less than a negative 1.645. Had this been a different alpha level, that would have given me a different z-score. This rejection region is tied to your alpha level. Okay? That was step number 2 so far. Now I'm going to go check your notes again. Step number 3. I'm going to collect the sample. Well, they already did that for us. But I'm going to compute the test statistic, which happened to be a z. So that z, you remember the formula, it was your score from your sample mean minus your population mean, or the hypothesis, mu in this case, that would be the number 3, divided by our adjusted standard deviation, S over the square root of n. That formula is always the same for a z when I'm looking at means. Proportions would be something different. So my sample mean, we found right here to be 2.9. That's my x bar. The mu, the population mean, is always the number in your null and alternative, which in this case is 3. Standard deviation is 0.2 divided by the square root of my sample size, which is the square root of 50. We would need to calculate that out. And if I do, it turns out to be a negative 3.54. That's a fairly extreme z-score. Let's just check it out again on this picture. Remember we said this was our line in the sand if it went over a negative 1.96? Well, notice we went all the way down to a negative 3.5. We actually went all the way over the line and almost way over to here. Our sample indicated that the average was way over here, negative 3.54. That's way over top this line in the sand. That would give me enough evidence to indicate that it can't be greater than or equal to 3. So I'm going to be able now to conclude that this is false and this one has to be true. That's our step 4. But notice how I made the decision. I took my z-score and I compared it to my rejection region. Because this z-score, this z was less than that number, it was in the rejection region. It went over our line. So here's my conclusion. Watch how I'm going to write it out now, because there's some really important terms that we should use. I start by repeating the z value, z equal to a negative 3.54 is sufficient evidence to reject our null hypothesis This z is sufficient evidence to reject our null. That's rejecting that it's greater than or equal to 3. And now conclude. What I'm going to conclude is this alternative, but I'm going to put it in context of the problem. So watch what I'm going to conclude. I'm going to conclude the mean number of hours worked on a part-time job by Northwestern students is, here I'm now concluding that it's less than 3, is less than 3 hours. Some statements that are really important in there. I had sufficient evidence to reject the null. That evidence was this number went over our line in the sand, and I now am able to conclude, that's a fairly strong statement, I can now conclude the alternative. A couple of things I want to highlight. Notice I numbered 1, 2, 3, 4. I need you to number those 4 steps on your work when you do a hypothesis test. If you were in class right now, I would tell your neighbor, I need to see the numbers 1, 2, 3, 4. If you don't show me those, you're going to lose points on your assignments as well as your tests. I need literally to have it numbered 1, 2, 3, and 4. So make sure that you do that. Number 1, I need those 2 hypotheses. Number 2, I need the alpha level, sample size, the statistic, and if it's a critical value test, I need a rejection region. Number 3, I need to show that where you got your z-score. Number 4, I need the conclusion. Notice how it's written out. It's always a paragraph. Don't just say sufficient evidence, reject, and conclude or something like that. If you have a context of a problem, write it out in context of that problem. I'm hoping after you see this whole thing that it's beginning to make maybe just a little more sense. On your next test, you're going to have 4 or 5 of these types of tests where you're going to have to show me all of this in a particular short answer. Some of your tests might have 2.9 hours, some might have 2.7 or something like that. Let's just say, for example, what if the sample mean had been 2.98? If it had been 2.98, then this sample mean would have been 2.98. That would have given me a different z-score. Actually, that z-score would have been the following value, a negative 0.707. It wouldn't have been nearly as extreme as this one. To give you a C of that, if it had been negative 0.7, that would have been right about here for a z-score. It would not have gone over the line. That sample would have been within reasonable variance of the 3. Then I would not have had enough evidence to doubt the null. I would not have had sufficient evidence to reject the null. So I wouldn't have been able to conclude that it was less than 3. What would I have written out in that scenario? If my z had been this number, number 4 would have written like this. Z equal to a negative 0.707 is insufficient evidence this time. I did not go over that line. I have insufficient evidence to reject our null hypothesis. So I will continue to assume, and what we continue to assume is always the null. So I continue to assume the average number of hours worked on a part-time job by Northwestern students is still, I'm going now and I'm assuming the null, it's still greater than or equal to 3, is still greater than or equal to 3 hours. Some key words: insufficient evidence, continue to assume, and I'm continuing to assume the null. Continuing to assume is not as strong a statement as we made when we were able to reject the null. If you remember the other one, we put down, I will now conclude. When I go over my line in the sand, I have a much stronger finishing statement. I'm making a conclusion. If my sample does not go over the line in the sand, like this one did not, then I just have to continue to assume the null. We're not proving the null is true. We're just saying we don't have enough evidence to doubt it. Let's say that again. If I don't go over that line, I am not concluding the null. I'm not saying that the null has to be true. What we're saying is we don't have enough evidence to indicate otherwise. So we continue to assume that the null is true. 2 different types of finishing statements, or number 4. Okay? I just described two types of decisions that we made in step 4. I've said this, but this is a repeat. If the z-score falls in the rejection region, that means we went over that line, we have sufficient evidence to reject the null, and we now conclude the alternative. It's a strong finishing statement. This will be accurate, or we say it's a correct decision, 1 minus alpha percent of the time. Do you remember in our previous example, we had alpha to be 5%? That was the probability of making it type 1 error. So 1 minus alpha would be the complement, or 95. In other words, in that problem, when I crossed over that line, I was 95% sure that the alternative hypothesis is true. That's what we mean by providing mathematical evidence. I would have been 95, 1 minus alpha, 95% sure that I could conclude the alternative to be true. And I would be right 95% of the time. Okay? When the z-score does not fall in the rejection region, that means I did not go over that line. If you remember, we said we had insufficient evidence to reject the null. We continued to assume the null hypothesis. That doesn't mean that we're concluding the null to be true. Doesn't mean we're stating that it's true. We just have to say we continue with status quo. We don't have enough evidence to indicate that it's false. This will be a correct decision 1 minus beta % of the time. We haven't talked about beta yet, but beta is the probability of making a type 2 error. You remember that alpha up here was the probability of making a type 1 error. This type 1 error was more serious than a type 2 error. It's also super important you recognize that these two, alpha and beta, are not, I repeat, are not complements. In other words, alpha plus beta does not equal 1. If alpha is 5%, that does not mean beta is 95%. In fact, usually both of them are fairly low. Usually alpha is considered to be lower than beta, so you might have alpha to be 5%, beta might be 15%. I'm breaking down now that step number 4 and looking at all of those possible decisions a little bit more closely. There are 4 possible outcomes. This 4 is different than step 4 in those notes. There are 4 outcomes. If the numerical value of the test statistic falls in the rejection region, that means I went over my line in the sand. Then I have sufficient evidence to reject the null, we said that, conclude the alternative is now true. That's a fairly strong conclusion step. We know that this will be correct 1 minus alpha % of the time. In other words, if alpha is 0.05, this would be correct 95% of the time. Alpha, though, is, in our previous problem, 5%. Well, it's possible that once in a while you just get a weird sample. It's in that 5% probability. And that weird sample went over our line. So we did what we expected to do. We rejected the null, we concluded the alternative. But 5% of the time, that's going to make an error. That's going to be called a type 1 error. If alpha was 0.01, then 1% of the time you'd make that type 1 error. Okay, visually, what is going on with that type 1 error? It would look like this. In that previous problem, we were testing against 3. Our line in the sand was over here at a negative 1.645. A type 1 error would occur when this happened. Normally your samples would be through here someplace. And if the samples started showing up way over here, we would get enough evidence to reject the 3. But sometimes the 3 might be accurate and we just happen to get a really weird sample. That could have occurred in that previous problem 5% of the time. If our one weird sample was over here, we would say, hey, I went over the line, I reject the 3, and I now conclude that it's less than 3. That would have been a type 1 error if 3 was actually true. This would be a case where we rejected the null that was actually true. 3 was actually the correct answer, and I rejected it. That would be a type 1 error. Okay? If the test statistic does not fall in the rejection region, we said we had insufficient evidence to reject. We sometimes say we reserve judgment, or we continue to assume. I'll be using this continue to assume, which I'd like you to do as well. So we continued to assume the null hypothesis. That will be correct 1 minus beta % of the time. Here's the type 2 error. A type 2 error can occur if I have inconclusive evidence, insufficient evidence, that's like saying that, to reject the null, but the null was actually false. I should have rejected it, I just didn't get enough evidence. It didn't go over my line in the sand. The probability of that happening is beta. This next slide puts it in just a real simple, short, nutshell version. These are the same 4 possible outcomes. If we reject the null, and the null is indeed false, that would be a correct decision. Because it was false, we rejected it. That would mean that my sample went over the line in the sand, I rejected the null, concluded the alternative, and the null was false, so I did it right. Great, that would be like 95% of the time. But here's that type 1 error. It went over the line in the sand, so I rejected the null, but the null was actually true. I just happened to have a weird sample. This would be an incorrect decision then if the null was true and I rejected it. That would be an error. We call it a type 1 error. The likelihood is our alpha. So in our first problem, the alpha was 5%. 5% of the time I would have said it went over the line, but the null was actually true and I rejected it. Not an error we want to make. A third decision, we failed to reject the null. I had insufficient evidence. It did not go over the line in the sand, but the null was false. I just didn't get enough evidence to detect it. This would also be an incorrect decision because the null was false, but I failed to reject that false statement. That's an incorrect decision. It's called a type 2 error. The likelihood is beta. And if it did not go over the line, I failed to reject the null, and the null was indeed true, that'd be great. Then I made the correct decision. So these 4 possibilities, 1 and 4 were correct decisions, 2 and 3 were errors, type 1 error, type 2 error. You should remember these words. So listen to me carefully once. Type 1 error. I rejected the null was actually true. I'm going to say that again. A type 1 error is I rejected the null and the null was actually true. A type 2 error is I had insufficient evidence to reject the null and the null was false. I'll say that again. A type 2 error is where I had insufficient evidence to reject the null and the null was actually false. This is like saying, again, they're not complements of each other. Another version, because it's hard for people to keep these straight, type 1, type 2 errors, here's another version. The true reality, which we seldom know 100% of the time, is either the null is true or it's false. Here, for example, I'm saying the null is actually true. If the null was true and I made a decision to reject it, that was a type 1 error. If the null is true and I did not reject the null, it was a correct decision. Cover that one up. If the null is false, my decision was to reject it, that was a correct decision. If the null is false and I did not reject it, that was a mistake. We call that one a type 2 error. Again, because these are mistaken so often, I'm hammering this as much as I possibly can. One more time. A type 1 error, rejecting a true null hypothesis. The probability of a type 1 error equals the level of significance or the alpha level. Type 2 error is not rejecting a false null, leaving the status quo, even though it was false. We just didn't have enough evidence to indicate that. We say a type 1 error is the more serious. Let me try to give you a different kind of context to help you understand why we say this one's more serious. In our country, in our judicial system, you frequently hear this line: in the United States, you are innocent until what? Hopefully you would say the answer is you are innocent until proven guilty. That means your no is saying you are innocent. It is up to the state to prove you guilty of some crime. Until they can prove you guilty, you are considered innocent. The reason they make that is they don't want to take innocent people and punish them, especially in a murder trial. In a murder trial, which is quite often done by a jury, the jury must be unanimous in a decision to make them guilty. If you got even one person on the jury that says, no, I believe they're not guilty, they cannot convict you of murder. They need a unanimous decision. That's because they want to make very certain they're not punishing a person for murder if they are in fact innocent. It's one of the strengths of our judicial system. Not every country has that. Some countries, for example, you get accused of murder, it is your responsibility to prove yourself innocent. You are guilty until proven innocent in some settings. Our country, thankfully, does not have that. We're going to practice right now just doing step number 1 in that set of notes that I asked you to print off. We're basically going to just practice on setting up null and alternative hypothesis. And then we're going to state type 1, type 2 errors. That's going to be the only thing you have to do on this first assignment, which is section 9.1. You'll be asked to set up null and alternative and state a type 1, type 2 error. So here we go with a bunch of examples. Over the past several months, Rayner & Sons have heavily advertised its electrical supply business. Mr. Rayner hopes that the result has been to increase the mean weekly sales above $7,880, which is what the company experienced in the past. What would I have to make the null and alternative in this problem if I were looking to provide evidence that supports the mean sales have risen above? That's what I'm trying to show. That means that's my alternative. The alternative is what I'm trying to show. I'm trying to show I want to provide evidence that it's above 7880. So I would put my mean to be greater than 7880. That's my alternative, which I usually list second. My null I list first in order. I actually come up with this one first, then go back and get the null. The null is the opposite. So the opposite of greater than would be less than or equal to 7880. That's all I would have to do to get my null and alternative. Now, what would be a type 1 error and type 2 error in context? That means connected to this particular problem. Well, a type 1 error was rejecting the null when the null was true. Think about that once, rejecting the null when the null is true. That's type 1. So here's what it would look like. A type 1 error would occur when I have sufficient evidence to reject the null. That's rejecting this one. So I rejected the null, and I consequently concluded that it was greater. So I concluded the alternative, when the actual truth was, it was still less than 7880. So the truth was this one, but I had enough evidence to reject that one and conclude that one. That was a type 1 error. Notice how long a paragraph I used to put it in context. You'll be asked to do that. You need to write out the whole paragraph. I'm going to say that again. You need to write out the whole paragraph when describing a type 1 error. Here's a type 2 error now. Remember again, a type 2 error is insufficient evidence to reject this when it was actually false. Okay, I should have rejected it, but I didn't have enough evidence. So here we go. Type 2 error would occur when I had insufficient evidence, means it did not go over that line in the sand, insufficient evidence to reject the null, when the actual truth was the null was false. It had risen above 7880, but I had continued to assume that that was still the case, and it was in fact false. That's a type 2 error. Here we go. Same song. Second verse. Hardee's, the fast food giant, was purchased by a company in California that planned to remove the fried chicken line from the menu. They feared the recent revenues had slipped below 4,500. To test the fear, they set up a null and alternative to provide evidence that supports their fear. I wanted to provide evidence that supported their fear. Their fear was that it had been below 4,500. Because I want to support that, I want evidence of that, that's my alternative. My alternative would be what I want to show. So I want to provide evidence that it's below 4,500. That would mean my alternative would be below 4,500. The null would be the opposite of less than would be greater than 4,500. Notice I do the alternative first, then I come back and write the null next. Describing what would be a type 1, type 2 error. Well, type 1 is rejecting this when it's true. Let's see how that reads. Type 1 error would occur. I had sufficient evidence to reject that null. I consequently concluded that it was less than. I concluded that it was less than 4,500 when the actual truth was it was still greater than or equal to 4,500. So I rejected the null when the null was true. But again, notice it's a long paragraph. You need to write out the whole paragraph. I say that again, you need to write out the whole paragraph. Okay, type 2 error would be I did not have enough evidence to reject this, but this one was false. I did not have enough evidence to reject it, but that one was false. Looks like this. Type 2 error would be I had insufficient evidence to reject the null when the actual truth was it had slipped below. I didn't have enough evidence to reject this one, but this one was false. That was a type 2 error. Again, notice I wrote it out. Okay. This is an example asking again the same thing, but it has to do with a two-tailed test. As a purchasing manager for a large insurance firm, I must decide whether to go with the upgrade for office computers. I've been told the average cost of this laptop, because we have a lot of apps that we want on it, is $2,100, pretty expensive. You wish to test that statement. So we take a sample of 64 retailers, find the average to be 2251, standard deviation 812. What would be our null and alternative to provide evidence to test whether it is, that's a key phrase. Notice I'm not trying to show that it's less than, I'm not trying to show that it's more than, I'm trying to show whether it is. That is word is screaming at me, two-tailed. The two-tailed means your null is always equal and it means your alternative is always unequal. That's locked in for a two-tailed. Now all you gotta do is put in the number. In this case, I'm testing against $2,100. Describe a type 1, type 2 error. Well, type 1 error is I reject this one when it's true. So that's what it would look like. It would look like the following. I'll read it right here. Type 1 error would be when I had insufficient evidence to reject the null. I consequently concluded that there was no longer equal to 2,100 when the actual truth was it was still averaging 2,100. That would have been a type 1 error. A type 2 error would occur when I had insufficient evidence to reject this one, but this one was actually false. I should have rejected it, I just didn't have enough evidence. That would have been a type 2 error. Two last things we want to cover on setting up null and alternative hypothesis. Read this one once. A recent issue of the Forbes reported exclusively hideaways in the upper New York State surrounding areas used by rich executives to escape the tedium of their stressful daily lives, blah, blah, blah. The cost is quite reasonable, the article reported. You can hire weekend accommodations for less than $3,500. I wanted to test this claim that it was less than, which would obviously take a random sample. I'm going to use a hypothesis test. Here's the key now. What would I use for my null and alternative if I wanted to provide evidence in favor of the claim? I wanted to find evidence to make a conclusion in favor of that it's less than 3,500. In favor means I want my alternative to be what they claim. So in favor would have had the alternative to be the mean is less than 3,500. The null would have been the opposite, that it's greater than or equal to 3,500. That would have been in favor. What if the problem had asked me to refute or contradict? To refute the claim means I would have been trying to find evidence that basically said that it is not less than 3,500. I would have wanted to show that the alternative was that it was greater than 3,500. Then I would have made the null that it was less than or equal to 3,500. The claim was less than 3,500. If I wanted to support the claim, I make my alternative the claim. If I want to refute the claim, I make my alternative opposite of that. It's important that you read these phrases carefully in your problems because they're going to use both types of phrasings in there. Try setting that one up on your own. I'm going to give you about 30 seconds, and then we'll be done. In favor would have given you this null alternative. If I wanted to set up a test to contradict it, I would have used this one. Now let's just say, because this is also kind of an important understanding, if I had tried to set up a test in favor, and let's say I didn't cross the line in the sand, means I would have continued to assume this. Let's say I had set it up to contradict, and I didn't cross the line in the sand. I would have had to assume this. If I couldn't show either one of them had sufficient evidence, it's why we say we go to the status quo. Status quo was 10.4 in linear times. We have no evidence that it's changed. That's what insufficient evidence would be about. It's why we call it status quo. That concludes our work for today. I'm assigning 9.1. This will be due next Monday, which I believe is it's March 30, I believe. Next Monday is the Dropbox. If it comes in after that, we have to count it late. Hopefully it'll be pretty well for you. I know that right now, so far, for many of you, this hypothesis test is pretty deep. Don't feel bad. That's true for most students the first few times. We're going to do so many examples that it's going to eventually start becoming much easier for you. So hang in there, keep plugging away. We'll look at a lot more examples the next time we meet. Okay? Have a good day.